Hi, this is Glenn Dane. I'm here on behalf of LIFT and the ASM Education Foundation. I'd like to give a little lesson on the value of lightweighting, really not just in cars, but really in all kinds of vehicles. And the real idea here is that sometimes it costs more to put lightweight components in vehicles, and we often get that back in fuel savings. I want to talk about that part. Also, if you reduce the weight of something, you generally are using less material, so there's also a win-win in there. So a well-designed, lightweight part is usually better than a heavy, old-school part, both because it's lighter, so it takes less energy to push the vehicle around, and then secondly, it uses less fuel because you have a lighter vehicle. So we have two simple objectives with this. Really, what I want to do is use this as a way of doing simple math with complex units, and complex units, as I'll show in a little bit, come up quickly, and if you're good with units, you're almost all the way to being an engineer, honestly. There's so many problems you can solve if you really understand how units work. And then the other thing you can do is you start to answer questions like, if I can save 100 pounds in a vehicle by using some kind of advanced lightweight component, but it costs me Y dollars, it might cost $50 to put in a component that's 100 pounds lighter, is it worth it in fuel savings? And a good recent example is Ford F-150 saved about 700 pounds by going to lightweight aluminum components. Aluminum has about a third of the density, we'll get into that later, of steel. And as a result of that, they saved 700 pounds, but it costs them a little more to put the aluminum in. Is that worth it in fuel savings? Well, we're going to answer that question. But first we have to do math in order to do that. And what we want to do is talk about units. Everything breaks down really into just a few fundamental units. The International System of Units, or it's often called SI units, there's 7 fundamental units. There's really a unit for mass, which is our kilogram, length, which is a meter, light, candelas, seconds and time, current and charge, amperes times seconds gives you amount of charge, Kelvin gives you temperature, and then numbers of atoms are counted in moles. With those 7 units, you can do just about everything. Things like magnetic field come out by basically having a current running through a given coil. So you can do all kinds of things like this. You have force, energy, power. And these are all basically just compilations of these basic units. That's an important part. Again, we're going to keep these lectures short. I'm not going to go into depth. You go into Wikipedia or many places on the web. You can get loads of depth on this. And the other thing, there's multipliers we put on these. And here are some of the more common ones. 10 to the 9 is mega. Giga, 10 to the 6 rather, is mega. 10 to the 9 giga. 10 to the 3 kilo. Millimeter, 10 to the minus 3 meters, for example. Micron is 10 to the minus 6 meters. And nanotechnology starts at about a billionth of a meter. So these are some of the big units that we use. And this is fundamentally the way it goes together. Again, I'm going to be quick about this. Hopefully you've seen this before. But if you can instill this in your students, there's a lot that you can learn in a hurry. And I did not want to do that. So I can get to the next page. So what we want to do is do a little bit where we convert units. And the key to converting units, treat the units as if they're variables or numbers. And then units can cancel from numerator to denominator, just the way we do with numbers. In the end, both sides of an equation have to be equal, so you must have the same units, or something is wrong if you don't. And then the units should make physical sense. If you're counting apples, it should be integers, or maybe even fractions of apples, but it should be apples. Counting oranges should be oranges. Doing length, everything should come out length, and so forth. Energy, and so forth. And we can go between these things. Okay. Just doing the math right. Again, a lot of this becomes very simple in a hurry. And so here are the key ideas. You can keep units, you can cancel them, you can always multiply by 1. For example, 60 seconds is equal to a minute. 2.2 pounds is equal to a kilogram. So you can multiply by these fractions. For example, 2.2 pounds per kilogram, or 1 kilogram per 2.2 pounds. These are both fractions equal to 1, so you can multiply by them. 0.62 miles is a kilometer, so you can take 0.62 miles over 1, and that's a fraction that you can multiply or divide with. So as a real simple example of this, let's ask the question, how many seconds in a day? So how many seconds in a day is a question. So we got 1 day, and we know that there's 24 hours in a day, and we know there's 60 minutes in an hour. And we know there are 60 seconds in a minute. And we can do our equal sign on that. Oh, geez. Bear with me. There we go. So what we can do is start canceling these things out. Cancel the days go away, hours go away, minutes go away, and we're left with seconds. And we do the math on this. We get 86,400 seconds in a day. Okay, so that's how many seconds you get in a day. So and the important thing here, each of these fractions that I multiply by is equal to 1, and that's what we do to keep all this together. So let's do a little more complicated example. Let's say you're riding your bicycle, you're going 12 miles per hour. How long at that speed will it take you to go 30 miles? So if you're doing that, you basically have 30 miles divided by 12 miles per hour. Miles cancel, and you end up with 2.5 hours. This thing is down in the denominator. In the denominator, it gets promoted back to the numerator. Another one you could do is your car gets 100 miles per gallon, or rather, your car goes 100 miles, gets 27 miles per gallon. Gas costs $2.86 a gallon. How much does it cost to go 100 miles? Well, let's see. You got 100 miles. Divide that again by 27 miles per gallon. And then you can multiply that by $2.86 per gallon. And then when you do the math on that, and more than my share of trouble with this. When you do the math on that, miles cancel, gallons get promoted up top, and this on the denominator would go to the numerator again. That cancels with that, and when you do the math, you get 10.1059 a gallon. And so that's our final answer. That's how much it costs you to take your car 100 miles. Well, what if you want a more fuel efficient vehicle? What if you want to have a lighter weight vehicle that would save you a little fuel? Well, we can value mass reduction, and a nice job was done. This comes from a nice book, Energy and the Environment, by Professor Michael Ashby at Cambridge University in England. He came together and found these metrics for what mass reduction really saves you if you have a lighter weight vehicle. So a proper metric, the metric we used before is miles per gallon. But really another good metric is, well, if you've got a 2-passenger car, a smart car can only fit 2 people versus a bus where you can fit 80 people. Passenger miles per gallon might be a better metric, even though a bus burns more fuel in total. If you're getting 80 people around, it's not burning 40 times as much as the smart car. Another thing you might do is consider how much energy it takes to go a given distance would be another good metric, or how much carbon is put out in a given distance. So what we start getting into are these complicated units. This is energy per distance, megajoules per kilometer. Well, a simple but effective metric that Mike Ashby came up with in his book, Materials in the Environment, is they show that there's a certain amount of energy it takes to ship a certain mass, a certain distance, and we can express that in kilojoules per kilogram per kilometer. So kilojoule is a unit of energy, kilogram is a unit of mass, kilometer is a unit of distance. And it turns out that different sorts of vehicles use dramatically different efficiencies in shipping mass. Turns out diesel ocean and diesel rail shipping doesn't take very much energy. You put a little more mass on there and it doesn't really matter. You get this up to speed once, that whole thing goes across the ocean or across the country, and it doesn't use much energy. So that you get numbers on the order of 0.1 to 0.3 or so kilojoules. An extra kilojoule is extra 0.1 kilojoules is used to ship an extra kilogram, an extra kilometer. If you have a personal automobile, it's about a factor of 10 higher. If you're using air freight, it's almost 10 times higher again. If you use a helicopter, it's about the worst of all in these things. And you can see if you lift something into the air, bring it back down, it's gonna cost you a lot of energy to do that. So let's do a quantitative example with this. And I'm going to be a little quicker than I was before. So from the last slide, if you have an automobile, a car, this takes about 2 kilojoules to take an extra kilogram, an extra kilometer. And that's what we had back from here. So personal auto, I'm actually at kind of the low side of that. Once there's 1.5 to 5, I'm picking the number 2, just for the sake of an example. So this is this here is basically the energy rate. I'm going to use below. So the question is, how much do we save by reducing auto mass by 10 kilograms? So this is the amount that I'm going to reduce at 10 kilograms. And what I'm also going to do is say, okay, a car, if I take that 10 kilograms out of the car has that lower mass for about 200,000 kilometers. That's a little over 100,000 miles. And so this is, the car's lifetime. So if I do that, I find out I have an energy savings of about 4 times 10 to the 6 about 4. Trust me, it turns into about 4,000 megajoules. So 4 times 10 to the 6 kilojoules turns into 4,000 megajoules when we're all done. So if I'm going from kilo to mega, this goes up, and here's why I did this, because I can put this in here and I can say 1,000 kilojoules, 1 megajoule is equal to 1,000 kilojoules. So when I make the conversion of 4 times 10 to the 6, I get 4 times 10 to the 3 megajoules, or 4,000 megajoules. So I can do the same thing here. The kilojoules cancel out, megajoules remain. I get 4,000 megajoules is what's saved in that unit form. Okay. It's funny, I just did that an hour ago and I already forgot what I did. So anyway, when I work that out, gasoline, there's about 130 megajoules in a gallon. So if I take this, and I'll leave this as an exercise too, I figure out how many gallons of gasoline I save over the lifetime of the car by saving 10 kilograms. So what I end up getting is that saves me about $30, or about $30 of gasoline. If gasoline's at $3 a gallon, saves me $90. I can also do some unit conversions in there and ask, okay, if I have $90, if I have $90 saved by 10 kilograms, what would it be worth in terms of dollars per pound? Well, it turns out for an automobile at this rate, the mass savings is worth about $4.50 a pound. And this is a number that the automakers use. This is how they make decisions on whether they or not they should lightweight a vehicle. Will it pay off in the long run? And will it pay off in the fuel economy? And there's lots of calculations you can do with this. And this is really the key to being sustainable, is do the math. Is it worthwhile or not? Okay. So we can go further with that and can consider all kinds of vehicles, as I kind of did back here a second ago. And we can consider all kinds of vehicles, personal auto, air freight. And again, if I go from personal auto to air freight, the amount of energy they use per length goes way up. Also, the distance an airplane goes over its lifetime goes up by orders of magnitude. So where things change by orders of magnitude, We can use our friend logarithmic scales. Logarithmic scales, here's our transport energy going from 0.1 to 1 to 10 to 100 kilojoules per kilometer per kilogram. And then also the service life of the vehicle. Buses may last 1,000,000 kilometers or so. Cars, that you're lucky to get around 100,000 out of them. I'm being optimistic here. If you take a locomotive, you might get 10 million miles out of it. Planes will fly millions of miles over their lifetime. So again, remember the way we did the computation. It's how much mass do you save, what's that rate of savings, and how far might the thing go over its lifetime. So if you take an example of an SUV, its transport energy might save on the order of about 5 kilograms per 5 kilojoules per kilogram per kilometer. That would put you about here. It might go on the order of 200,000 miles. It'll put you here. You can do the computation. Let's imagine that spot is here. That's going to be maybe again like $5 a pound, or about 20 liters of gasoline saved over that on a per kilogram basis. So you could put a spot on this thing. If I make a locus of spots, I can put them on here and have a line here. At this line, I save $13 per gallon, or about 30 liters per kilogram saved. So again, for each of these things, this is the amount of fuel. Excuse me. This is the amount of fuel. This is the weight savings that you have. These top ones, I put them in the same line. This is the cost savings, and this is the mass savings in different units, in pounds units. So the point is, for cars, you have a modest amount of weight savings, a modest amount of energy savings per weight, and they don't go that far. If you take an airplane, you actually have a much higher cost of moving stuff around, and they go much further. If you do the math there, you're talking about somewhere between about $1,000 saved per pound removed, and maybe $10,000 per pound saved. This is because every time the airplane goes up in the air, you've got to lift that mass, accelerate it to a high speed, 500 miles an hour, slow it back down. Lots of mass, lots of energy is saved by that small mass reduction. Okay, get it? I hope so. Point is, cars take a modest amount of energy to push mass around. They don't go that far. You get numbers on the order of about $5 saved per pound pulled out of the car. If you're doing this in an airplane, it's thousands of dollars per pound pulled out over the life of the airplane. Okay? And I think my slides are slightly out of order. They are. So this is the last real technical slide on here. This is one I kind of like. This on the bottom of this slide, you've got various materials going from really cheap ones to really expensive ones. Cheap ones being concrete, expensive ones being gold and platinum. And on a log scale, these go from about $1 a pound to about $10,000 per pound. And on the top, you've got various vehicles. And we can also figure out what they cost on a per pound basis. A typical car goes at about $10 a pound. Cheapest bike you can get goes at $2 or $3 a pound. Commercial jets, if you work it out, they go at about $1,000 a pound. So this has a lot to do with what kind of materials make sense. If you're selling a car at about $10 a pound, and you've got carbon fiber composite that you want to use, and it's still selling at $50 a pound, you're going to have a hard time making that work for a large fraction of the vehicle mass unless you do something pretty special. You've got to maybe really reduce the vehicle weight. So there are real quantitative decisions that you can make to make all of this come together. How much will you save? How much can you benefit? And what do the base materials cost? There's actually a whole lot in there, and I'm not going to go any further than that. But what I do want to do is conclude here. Say mass reduction does save energy in vehicle use. We can make some good estimates, and I've hopefully taken you through enough where you could make these estimates for yourself. For a car, we can save several dollars per pound saved, and for something like a commercial airplane, we can save several thousand of dollars per pound saved. And you can calculate this, and that also lets you know what materials are really fair game. For cars, you're not going to be using highly exotic materials, but for airplanes, you can. Hopefully that made some sense. I'm going to stop there and would welcome any questions over the internet, and we'll see you later. Take care. Bye.